Hello, world. This is CS50, and this is CS50's Fundamentals of Artificial Intelligence with CS50's own.
I'm Brian Yu.
So like the past couple of days, we have been live streaming these lectures as we're filming them for the very first time. I'm going to be sitting in back, taking any and all questions via the chat, and raising my own hand on your behalf to verbalize some of them to Brian. Today's focus, though, is our very last lecture in this series on what
It'll be all about moving, taking AI into the physical world, thinking about technologies like robots and self-driving cars and what kinds of challenges arise there.
And we've been doing this fun fact thing now the past few lectures. Brian, have you ever been in a self-driving car?
I have. My family is from the San Francisco Bay Area. I was visiting them a few months ago and got to ride in a Waymo for the first time. So yeah, enjoyed the experience. Yeah, it was pretty impressive.
Excellent. They're coming to Cambridge, apparently. They've been testing them in the city that Harvard itself is in. So we shall see how soon that happens. Separately, we're about to film a 30 to 60-second introduction to the course itself. So we're going to get all formal for a moment. I'm going to say a few remarks. Brian's going to say something specifically about the class. Then we're going to pause, and then Brian will kick off the real lecture itself. This is one of two, what we decide. This is one of two courses on artificial intelligence.
Yeah.
OK. And this time, I'm going to say with CS50's own Brian Yu, I'll just say your name so that I say my sentences and then turn it over to you.
OK.
OK. All right. Ready when you are, Scully? Hello, world. This is Oh, sorry. Messed up already. Hello, world. My name is David Malan, and this is CS50's Fundamentals of Artificial Intelligence with CS50's own Brian Yu. This is one of two courses by CS50 on artificial intelligence. The first, CS50's Introduction to Artificial Intelligence with Python, is a programming class for those with prior programming experience. This course, though, CS50's Fundamentals of Artificial Intelligence, is for anyone who wants to learn about artificial intelligence. No programming experience required. You can take this course either before, during, or after any of CS50's other courses.
So this class is going to be all about exploring some of the ideas and strategies and algorithms behind how artificial intelligence works. We'll be looking at how we can use AI to play games, make predictions, analyze data, communicate with natural language, generate new content, and move about the physical world, all with the goal of helping you develop an understanding for what artificial intelligence really is and how it works. So we hope you'll join us. This is CS50's Fundamentals of Artificial Intelligence.
Was that OK having the slight pause?
Welcome back, everyone, to Fundamentals of Artificial Intelligence. And now, in today's final lecture, we'll be exploring some of the challenges around bringing AI into the physical world, so that AI doesn't just live on our computers and our phones, but you might think about applications like robots and self-driving cars, where AI has to navigate and move about the physical world. And we'll be thinking about some of the challenges that come about when we're trying to get AI to navigate in the real world itself. And so what are some of the challenges that we might start with? Well, let's start with something simple, and let's start with the problem of path planning. The idea that if we want AI to be able to navigate around the real world, it's currently in some place, and it wants to get to some other place, and we need some way for the computer to be able to figure out a path to get there. And we'll start with a relatively simple world, but over time today we'll introduce some additional constraints and some additional challenges to this problem as well. So we'll imagine that we have a world that's just this grid of squares here. We've got this 5 by 5 grid of squares. And we have some walls, some constraints, some obstacles that we aren't able to pass through. And we imagine that we start at one of the places in this grid. Maybe our AI starts in the bottom left corner here. And we have some goal, some destination that we'd like to get to. Maybe this star over here is the goal for where we're trying to reach. And the problem of path planning, then, is to be able to find a path that will take us from where we are now to the goal. And there are a variety of different algorithms that we could use for trying to solve a problem like this. But let's start with a simple one called depth-first search. So what is depth-first search? Well, it's a search algorithm that will try and find us a path from our starting point to our destination. And it does that by just trying a path. And the general idea is that when we run into a dead end, if we try a path and we find out it doesn't work, it doesn't lead us to where we're trying to go, then we can back up and then try something different as a result. Let's see what that looks like by taking a look at this grid here. So we're starting here from this initial state of this grid. And initially, we have two directions we could go. We could try going up, or we could try going to the right. And initially, our AI doesn't really know which way is the right way to go. So it's just going to pick one at random. So maybe we'll try going up first. And we'll just keep following that path and see where it leads. We go up, and we'll just keep following that path. We'll go up again. We'll go up again. And we can keep following the path. We don't really have any decisions to make yet, because we've just chosen one path. And for now, we're sticking with that path and seeing where that particular path will lead us to. We'll take a step to the right, take another step to the right, take one more step to the right, and now we have a choice again. We could either choose to continue to go to the right, or we could choose to try going down. And again, depth-first search, or DFS, as the algorithm is often known, doesn't really know which way is the right way to get to the goal. We can check to see if we're at the goal now, which we're not. But we don't know which way is the right way, so we're going to pick one and we'll try it. Maybe we'll try going to the right, and we'll try going to the right, and at that point, we've hit a dead end, right? There's nowhere further that we can go along that path. And so what are we going to do? Well, clearly that wasn't the right choice to make, so we'll back up to the previous point where we made a decision, which was here, and we'll instead try exploring the other direction. We'll try a different path instead. So we'll try going down. We'll go down one more. We'll end up here. Now we've got three choices for possible directions we can go in. We could go to the left. We could go to the right. We could go down. So again, we'll pick one. We'll give it a try. Maybe we'll try going to the left. Again, we've hit a dead end, but that's OK. Anytime in DFS we hit a dead end, we'll just back up, try something different instead. And so maybe this time we try exploring to the right, and we find out that we have, in fact, found our destination. So what the AI is going to be doing is that if it has all of this information as input, what the world looks like and where the obstacles happen to be, we can engage in some path planning. Before the AI ever moves even the first time, we can start to understand what possible paths there are and use an algorithm like DFS to be able to find a path that will end up leading us to our goal, to our destination. And once we found a path that goes there, then we can have our AI robot, in this case, follow that path and go along the path we found that leads to that destination. So DFS was able to find a path for us. But one question that you might ask in this case is, did it find the optimal path? And when I say optimal in this case, I mean the shortest path. That ideally, if you're trying to figure out how to navigate about the physical world, you don't just want a path to get to the goal, but you want a good one that's reasonably short. You might imagine that if you're using a car navigational system and it's trying to navigate you from one place to another, you care about getting to your destination, yes, but you also care about getting to your destination quickly. If there's a shorter path and a longer path, you probably care about finding the shorter path if you can. And if we look at this case here with our duck, it did find a path, but did it find the shortest path in terms of the number of steps that it could take? And in this case, it doesn't seem like it did. I might argue that there was, in fact, a shorter path we could have taken, which would have been to say, starting from this position, instead of going up and taking this longer, winding route to the destination, we could have instead started by going to the right and found a shorter path that way that would have gotten me to the goal in just 1, 2, 3, 4, 5, 6 steps in this particular case. And so DFS found us a path, but it didn't find us the shortest path. So we might like to explore some other algorithms that would be able to help us find the shorter path if a shorter path does in fact exist. And so an algorithm we can try to use for that is one known as breadth-first search, which takes a little bit of a different approach. Breadth-first search, or BFS, takes the approach of instead of just trying a path at random and seeing where it leads and then backing up if we run into a dead end, which could find something that works but might not find the best route, it'll start by looking at all of the possible shorter paths first. We'll look at where can we get to with a distance of 1 from where we're starting, and then where can we get to with a distance of 2, and then a distance of 3, and so forth. And we can explore what that looks like in the context of the exact same grid. We'll start here in the lower left corner. And whereas in DFS, the approach we took was to say, pick a path and just try it until we reach a dead end, BFS is going to say, how far can we get by just moving 1 square from our initial state? And we can see, well, there are 2 places we can get to within 1 square. We might try this one first, and then we might look at that one. Neither of those was the goal, so we clearly can't get to the goal by taking only 1 step. But then we'll consider, all right, well, where can we get by taking 2 steps? What are the possibilities? So from each of these states we can get to, if we take 1 additional step, where could we potentially arrive at? Well, from here, we could move up 1 and get here. And from this one to the right, we could move 1 to the right and get here. So rather than just exploring 1 path until the end, we're sort of exploring all of the paths at once, looking at shorter distances first, and then expanding to longer distances. So after exploring where we can get to in 2 steps, clearly it doesn't lead us to the goal just yet, then we'll increase that distance again. We'll say, all right, well, where can we get to by taking 3 steps? So from 2 steps we could get here. In 3 steps we can get 1 spot further over there. Again, here from 2 we can go 1 step further to 3. And if that doesn't lead to the destination, we can try again. We can say, all right, well, from each of those points that we can get to in 3, how far can we get to by taking 1 more step with a distance of 4? Well, we can get up here, we can go here, and we can go there, and repeat the process. In 5 steps, we could get to here, or we could get to this square over here. And then what about in 6 steps now? Well, if we can get to here in 5, then we can take 1 more step and get to 6 here. And then from here in 5, we can take step number 6 and either go to the left, or we could go to the right potentially. And once we've done that, maybe we'll find that, all right, now we have in fact found our goal. And because we started by looking at the shorter paths first, we looked at how far can we get to in 1 step, and then 2, and then 3, and then 4, and then 5, and then 6. Once we've reached the goal here, we know that there isn't a shorter way. We have in fact found the shortest way to get from our initial state to that goal that we're looking for. And it turns out in this case, we can do so in 6 steps. So BFS is exploring each of the paths a little bit more slowly, because we have to sort of go back and forth between each of the paths, checking as we go longer and longer to see if we're able to get to our destination. But it is able to find the shortest path in each of these cases to be able to make our way from where we started to the goal, to the destination we're trying to reach. And so you might imagine using this kind of a technique to figure out how you might navigate around the world if the world is this grid with obstacles in the grid. But in reality, the world is a little bit more complicated than that. And so what we're going to be looking at throughout today is some of those additional complications. What are the challenges that arise, and how are we going to deal with those challenges as we're figuring out how to get AI to navigate around the physical world? Now, one constraint we can relax a little bit is that the world doesn't necessarily need to be this grid where our only options are to move up and down and left and right. We could instead represent this world as just a bunch of different states that we're going to represent as these individual circles. You might imagine these being like intersections in a city, for example, or maybe different towns that you're traveling between on a long road trip, for instance. And then we're going to draw connections between these individual states, or nodes as we might call them, for which states can you travel between. I can go from this node over here to that node over here by traversing this edge here. Or, for example, I could go from this node to this node by traversing this edge. And so this is a little bit more of a generalized form of the problem we were looking at before. Before, it was a very fixed grid where you can always go only up and down and left and right. This is what we call a graph data structure in computer science, where we have these nodes that are connected to each other via connections, otherwise known as edges. And if we have this graph of nodes and edges, then this path planning problem becomes a problem of how do you get from the starting node, maybe we're starting over here, to some destination node. Maybe we're trying to get over to the blue star over here. And so the question is, how do you get from our starting node to the destination node just by traversing through these edges? We can only follow an edge to get from one node to another. So I can't jump directly to this node over here, for example, because there is no edge connecting those two nodes. And so I could try the same algorithms and use them on this graph data structure instead of on the grid. So if, for example, I was to use depth first search, or DFS, to try and go from my starting position to my goal, well, then I'll start here. And remember, DFS just starts by choosing a path at random, following that, and seeing where it goes, backing up if we ever run into a dead end. And from here, I have 3 different options, right? 1, 2, 3 different choices for where I can go. So I'll sort of pick one at random, and we'll follow that and see where it goes according to DFS. So in this case, I only have one choice. I'll just keep following the path. I'll keep following the path. I'll keep going. And if I go over to this state over here, and I've reached a dead end, there's nowhere further I can go from this state. There are no other edges that will lead me to some node that might come next. In that case, I'll back up. I'll go back to this node over here, and I'll try a different direction. Maybe try going down. And again, here I have choices, multiple choices for where I can go. DFS doesn't know which one the right one is, so I'll make a decision. I'll try going one place. That one seems to also lead to a dead end, so we'll go ahead and back up, and we'll end up finding that maybe now we can find our way to the goal. And as we're going about this process of running an algorithm like DFS, every time we arrive at a new node, we can keep track of where we came from. When we get here, we know that we came from here. When we got here, we know that we came from this node over here, and so on and so forth. And so once we found our way to the goal, what we can reconstruct is what is the path that we need to take in order to get there. So in this case, once we found the goal, we know that we can have our AI duck here follow that path in order to make our way from the starting point to that goal. Once again, DFS was able to find a path to the goal, but it didn't find the shortest path. So we could use our other algorithm, breadth first search, or BFS, to make sure that we find the shortest way to get to the goal instead. So what would that look like? Well, remember, the BFS starts by looking at the shorter distances first. We'll say, where can we get to if we start here and we only take one step? Well, I have 3 options for where I can get to. I can get to here. That's one option. I can get to here in one step. And I can also get down here in one step. All of those are possible. And then we'll say, OK, we haven't reached the goal yet, so let's go a little bit further. Let's say, where can we get to in 2 steps by going to any of these states and moving one additional connection forward? Well, from here, I can move 1 forward and get to here. From this state that I could get to in 1, I can move 1 forward as well. From this state, I actually have 2 choices. I have 2 places I can get to with a total distance of 2. Right? I got to here in 1, and then I could get over to here in 2. Or I could follow this edge along the bottom and get to this state in 2. So those are possible places I can get to in 2 steps. And then we can say, all right, what about 3 steps? That will take us maybe here from this node over here. If I can get to here in 2, then I can take a 3rd step and get here. If I can get to here in 2, I can take a 3rd step to here, and then repeat the process for 4 steps as well. From this state, I can get over here in 4 steps. And if I can get here in 3 steps, then I can get to our destination in just 4 steps, which is faster than I was able to find before. And so now I've found my shortest path, that using just 1, 2, 3, and then 4 edges, I can make my way from the starting point to the destination. And so you might imagine using an approach like this, if you imagine that these connections are roads that travel between different places in a city or a collection of cities, that you might find your way from one location of interest to some other location you're trying to get to, and figure out what is the path that you can take that will require the fewest roads, for example. But not all roads are created equal necessarily. Some roads are going to be longer than others. Some might have tolls on them where you have to pay some fare in order to go through them, for example. Some might have traffic that are just going to slow you down, and you might be aware of that. And so you might take that into consideration as well. And so one additional piece of information that we might try to add to this problem is to give each of these edges what we call a weight or a cost. So we give each of these edges a number. And this number here represents the cost of taking that connection, of moving from one node to another along that particular edge. And you might imagine that cost being a cost in time, like how many minutes it takes to get from one place to another. It could be a financial cost, like how much it actually costs in energy and resources in order to get from one place to another, or some combination of those. But just think of the cost as something that we want to try to minimize. We want to minimize how many numbers we'd have to pass through, the total sum of those numbers that we'd have to pass through in order to get from our starting point to our destination. And now, neither depth-first search nor breadth-first search is really handling these edge costs, right? Breadth-first search is going to find us the way to get from our starting point to our destination using the fewest edges, right? We found the path that went 1, and then 2, and then 3, and then 4. But the total sum of all of those costs was 3, and then 7, and then 2, and then 1, for a total of 13. That would be the cost of taking that path that we just found before. And so now we might ask, is there a way to get from the starting point to the destination in a lower cost way that doesn't use as many resources or time or money, for example? And it turns out there's another variant on this kind of algorithm we can use for solving exactly that. And the algorithm is known as Dijkstra's algorithm. And here's the way it's going to work. It's going to work by trying to prioritize the nodes that we can reach at a lower cost first, and then look at the ones with higher cost. So we start from our starting point here. And from our starting point here, we have 3 choices for where to go. Now before, DFS and BFS, when faced with this choice, 3 different paths of where to go, they all were pretty much equivalent to each other. So we could just pick one at random and try it if we had a bunch of equivalent choices to make. Dijkstra's algorithm now, in this case, is going to look at this situation and say, well, if we have 3 choices, one that costs 2, one that costs 4, and one that costs 3, let's prioritize the nodes that I can reach with the lowest cost first. So between 2, 4, and 3, I'm going to prioritize exploring the node that I can get to with a cost of 2. So we'll go ahead and go there first. And now that's going to open up some additional options. Now I could potentially explore this node here. And to get here, it would be a total cost of 5, right? 2 to get here, and then 3 more to take this edge here. And so if it costs 5 to get here, but only 4 to go here and 3 to go here, well, this 3 is the lowest cost option I found so far. And so that's going to be the thing that I explore next. So we'll next explore this one over here, which I can get to with a cost of 3. And at this point, I have finished exploring things I can get to with a cost of 2 and with a cost of 3. But I have a few different options for what I can explore with a cost of 4. I could explore this edge over here. I can get here with a cost of 4. Or I could take this pair of edges here, cost of 3 to get to this state, and an additional cost of 1 to get to that state over here. Both of those have a cost of 4. So we'll explore those next. We'll go here with a cost of 4, and then we'll go down here with a cost of 4. The order between those two is kind of arbitrary. And now we'll say, we've explored things we can get to with a cost of 4. What about with a cost of 5? So we're saying, of the remaining ones, we see that this one has a cost of 5. This one also has a cost of 5. But this one here, that has a cost of 10. It'll cost 3 to get here, and then 7 more to get to this state over here. So what Dijkstra's algorithm is constantly doing is looking at all of the states I could potentially get to next, and then prioritizing which one should I try to explore first based on which one has the lower cost. And so between 2 nodes that I can get to with a cost of 5 and 1 that's going to cost me 10, we'll go ahead and explore the 5s first. So we'll explore this one over here and this one over here. And we'll continue that process, asking the same question. What are the reachable states that I can get to next? Well, I could, from here, get to this state over here. That will cost me 2 plus 3 plus 2 for a total of 7. Or I could go from this state to this state over here. That'll cost me 4 plus 1 plus 9 for a total of 14. Or from this state I can get here for a total cost of 3 plus 7. That'll be 10. And so given all of those options, the cheapest option, the one with the lowest cost, is actually this top path over here. 2 and then 3, which I know takes me 5 to get here, and then 2 more in order to get to that state over there. That will be a total cost of 7. We'll try exploring that. And from there, we can repeat the same process. These two seem like they're more expensive to get to, but I can get to here and here with a cost of 8 just by 7 to this node here, and then 1 additional step to get to either one of those. So we'll try exploring those, and then we'll discover that with a cost of 9, I can get to this goal over here. And so what Dijkstra's algorithm has found for us is the path not the one that requires the fewest connections, but the one that is the lowest cost. That if I'm trying to evaluate what's the way to get to my destination that's going to minimize the fuel that I need, the resources that I need, the time that I need to spend, whatever it is that I'm trying to prioritize, if I can assign a cost to each connection, then I can find the path that will take our agent from our starting point to our destination with the least cost. In this case, we found one that takes an edge weighted 2, and then 3, and then 2, and then 1, and then 1, for a total cost of 9 in that case. And so algorithms like Dijkstra's algorithm we can use to try and find a shortest path in order to get from our starting point to our destination. But one thing you might have noticed is that this algorithm took us a little bit of time. It took some time to process constantly what is the node that we can get to with the least cost, and then to explore those possibilities. And we explored a bunch of possibilities that didn't really lead us in the right direction. And so maybe there's some optimizations we can make if we really want this to work in the real world. That in the real world, if you've got a robot navigating the physical world, it might not have a lot of time to be able to figure out what is the path, what is the plan to get to the destination for where I'm trying to get to. We might like something a little bit more efficient. So let's look at those efficiency issues and try and figure this out. We'll return back to this grid-like maze here. And so BFS and Dijkstra's algorithm, these sorts of algorithms can definitely find us the optimal path, the shortest path to get to the destination. But the question now is, how quickly can it find that optimal path? How much time does it need to spend thinking and planning? How much do we need to explore before we're able to find that path that is going to be the most optimal one, the best one? And so let's explore what an algorithm like BFS or Dijkstra's algorithm will do in this case if we're trying to navigate this grid, trying to get from our agent here in the middle over to the star in the lower right corner. Well, remember that in an algorithm like BFS or Dijkstra's algorithm, we're going to look for the low-cost options first. We're going to start by what can we get to with a distance of 1, in this case in the grid, if you assume that every connection between these grid cells has the same cost. We'll start by saying, what can we get to with a distance of 1? We can get up here, or we can go down here. And then we'll say, what about with a distance of 2? Well, we can go up here, or we can go to the left here, or we can go down from here. And then in a third step, from here I could go up to here in a third step. From here I could go left in a third step. From here I could go right in a third step. And you can imagine how an algorithm like Dijkstra's algorithm will continue to run from this point forward. It's just going to keep exploring the lower distance options first, building up to higher distances, until it eventually finds us a path that will take us from our starting point to the goal. And what you'll notice is that what it found is in fact the shortest path. It is the optimal path, that this is the quickest way to get to the goal. There were other slower ways we could have taken, like going up and around and about in order to get to that goal. But it had to do a lot of work to get there. If you look at all these yellow cells are cells that we had to explore in order to calculate what the optimal path was. And we ended up exploring a lot of stuff up here and a lot of stuff over here to the left. And you might imagine if you were the one trying to solve this maze, for example, just trying to navigate your way over there, you probably wouldn't spend a lot of time exploring the left half of the maze because, well, the direction you're trying to go is to the right. So maybe you should try to bias your search process to prefer options that are going to take you closer to the goal. And so this is where we can introduce a different style of search algorithm known as an informed search algorithm. So what is an informed search algorithm? An informed search algorithm is one where instead of choosing randomly, when we have a bunch of seemingly equivalent choices, we're going to use some information about what we know about our goal and how likely it seems like we're going in the right direction to get there in order to bias our decision making to prefer exploring states that seem like they're going to be closer to our goal. So how could we go about doing that? Well, in this case, we might start from our starting point here and say we have two options for where we can go. We could go up and we could go down. And before, I've been saying that if you've got two equivalent options, both a distance of 1 away, it doesn't matter which you explore. Just pick one at random. In this case, we're not going to pick one at random because we're going to evaluate these a little bit differently. We're going to evaluate them based on a heuristic of sorts. We're going to say which one looks like it's probably going to be closer to the goal. And how could you evaluate whether it's probably closer to the goal or not? You could evaluate that maybe just based on, is it in the right direction? Like, does it seem like if we're here and the star is down there, it's one row beneath us, do we want to be going one row up or do we want to be going one row down? Well, it seems like we want to be going one row down because, yeah, there might be walls in the way, but going down brings us closer to the goal than going up does, just in terms of physical geometric distance. And so if I have a choice between going up and down, well, I'm going to prefer going down, because that seems to be the direction that's going to take me closer to the star, even though there might be walls in the way. So what do I do now? Well, now, from here, I've got some options, but neither of them looks great. Like, I can take a step to the left, but that actually seems to be taking me away from the star. Or I could take a step that goes down, but that also doesn't seem to be quite right. I'm in the same row that the star is in, so going down, that's moving me one row away from the star. That doesn't seem great either. And then going up, well, that also takes me one move away from the star. And so sometimes we're going to find ourselves in situations where maybe we do just try going up a row, because it doesn't seem like we can immediately take a step that will move us closer to the goal immediately. Or we'll try going to the left, or we'll try going down and just see what new options show up. And now if we look at our remaining options, we could take a step here. We'll have taken 3 steps, and we'll be like on our way, moving in the direction of that goal. So that seems pretty promising. Or we move 1 step up here. That seems to be moving us further away from the goal. That doesn't look good. And likewise here, moving 1 step to the left also seems like it's moving us away from the goal, which doesn't look great. And so maybe we'll follow this option, take a few steps that way. And again, we're faced with some choices. We can go up or to the right. In this case, both of those look pretty good, right? From here, the goal is both 1 row up, and it's to the right of us, so going up or to the right. Both of those seem like reasonable options. So we might try them. We might try going up. We might try going to the right. Going to the right, it turns out, seems promising, right? We can move to the right, get closer to the goal, but we end up running into a dead end. That's OK. We can start exploring some other options too. And in this case, again, all of the options don't move us directly in the direction of the goal. Going up here takes us to the wrong row. We're already in the right row of the star, so moving up seems to be moving us away. Same thing goes for these 2 states here. So we might try exploring a little bit, just seeing, do any of them open up some options that are going to lead us closer to the goal? But eventually we'll find that, all right, from here, now we can really start taking steps that take us in the right direction. We can go to the right. That's bringing us closer. That's bringing us closer and closer. And then finally, we can go down and find our way to the goal. So the idea of an informed search algorithm like this is to say, if we take into account information like how close do we seem to be to the goal at any given state, I can avoid needing to spend all my time exploring this whole left side of the grid and this top side of the grid, because I've biased my search process towards the paths that I think are going to be most promising. I ended up finding the same path, but I was able to find it much more efficiently. Yeah, a question.
When you were only 4 blocks away from the goal, would it not have made sense to bias your search by continuing to focus on the block closest already to the goal, as opposed to going back up to the top or over to the left?
Yeah, so if we go back a little bit, if we go back to a spot like this, might it have made sense, instead of searching up this way or left this way, to just prioritize this one that already seems like it's closest to the goal? Yeah, we definitely do want to prioritize being closest to the goal, but we also want to take into consideration, if we're looking for the shortest path, that we also need to take into consideration how far we've already traveled in order to get to that point. That if it took us 1, 2, 3, 4, 5 steps to get to the point, this point, and then it seems like it's the closest to the goal and we might still have some work to do, whereas this one over here is not all that much further from here, but we only had to take 1 step to get there. We've exerted like less effort to get here, whereas it took 1 step to get here and maybe 5 or even 6 steps to get here. So at that point, we have to balance those 2 concerns and say maybe we do need to spend at least a little bit of time exploring this path that we just haven't traveled as far along, to see if maybe that will end up leading us to something better too. And so algorithms like the one that I've shown you, and this particular algorithm is an algorithm called A-star search. And there are a variety of different informed search algorithms like it. But A-star search is an algorithm that balances between those 2 things. It balances between how far have we already traveled, and it balances between that heuristic that we were talking about, which is how far do we potentially have left to go, based on our best guess as to how far away the goal happens to be. And so algorithms like A-star are particularly popular for trying to figure out path planning. And there are even more variants that we might introduce in order to deal with possible complications that might come up in the real world. What are some of those complications? Well, for example, we've been assuming that the world is this fixed static grid with fixed static obstacles. In reality, that might not always be the case. If you're a robot navigating the world, people are going to be moving around, objects might move, the obstacles might change. If you're a self-driving car navigating through the world, you might know what the roads are, but roads might suddenly close or get blocked off, or obstacles might show up in the way. And so the environment is dynamic. The environment might change. And so you might calculate what the optimal path is, you might figure out that the right way to go is to go down and around in order to get to that goal. But as you take one step down, a new obstacle might show up. Maybe an obstacle shows up there. And at that point, you're going to need to replan. You're going to need to figure out, all right, the path that I had before is no longer going to work. I need to come up with a new plan and sort of replan on the fly and figure out, all right, now the right way to go is going to be to go up and around. And you'll have to adapt on the fly too. Maybe some of the existing obstacles will go away, opening up new paths. And you can say, well, now, whereas before I was going to go around, now there seems to be a shorter path to the goal instead. And so I could try following that too. And so one option would be like every time the world changes and the obstacles change, you could rerun an algorithm like A** search to be able to figure out what to do. That can sometimes be a little bit costly in terms of just the time it takes to constantly have to rerun a search algorithm again and again. But there are optimized versions of the process with algorithms that are called like D* and D* Lite, which are meant to only recalculate the things that it needs to recalculate, to be able to very quickly and very efficiently, when the obstacles change, figure out what is actually going to change about the potential path that you need to take. And so adapting to those variety of different obstacles is one thing that we'll be able to think about using these kinds of algorithms as well. And so now let's move from the world of path planning to a slightly more challenging problem of motion planning in general. So while path planning is just about figuring out, is there a path to getting from where I'm starting from to where I'm actually going to, motion planning starts to deal with the realities of the physical motion of objects in the world. That sometimes it's not just enough to figure out that there is a path to the destination, but we actually need to plan how it is that the object is going to move to that place. And so let's take the example of self-driving cars, or just take the example of cars in general for now. Imagine that we're a car, we're this blue car over here, and we want to park our car in between all of these other cars that are on the road here. Well, if we just think about this from a purely path planning perspective, we're here, we're trying to get here. We might imagine that we just want the car to move down, for example, and that's what we want the car to do. And while that works in a geometric sense, it probably doesn't work in a physical sense, that the car, because of the way the wheels are pointed and the just orientation of the car just can't literally move down like that, even though if you were to draw a grid like the grids we've been looking at, these are adjacent cells in the grid. They appear to be next to each other, but the car can't literally just move from one cell to another. There's a more complex path motion planning process that's going to be involved here, where we need to figure out where exactly does that car need to move, what angles does it need to use, and how does it need to adjust those angles in order to get from our origin point to our destination point, the place where we were trying to go. And so here, we might try to define the configuration of the car. How would we describe the state of the car? And the state of the car in this case is described not just by its like x and y coordinates of where is it in this coordinate grid, but in this case also by like the angle, what direction is the car pointed in, that all of those are going to be relevant facets of determining how the car is configured. And in reality, you might add even more data into this configuration, where things like which direction the wheels are pointed or what gear the car is in. All of those are pieces of configuration of the car that determine what kind of states you can get to next, what kind of motion is actually possible from there. Or if we think instead of cars, we imagine like a robotic arm, something like this, and imagine what would it take to do some kind of motion planning here. Ultimately, I want to be able to say, like, take the head of this robotic arm and move it here, or move it there. But it's not so simple. We can't just immediately say, move the head here or there. We need to figure out what are the actual pieces of this machinery that we can control. What are the things we can configure? And in this case, this robotic arm is configured by 4 different joints, it seems. We have a configuration point here with an angle that we can adjust for which direction we're pointed here. We have a second configuration point here with another angle that we can adjust for where that can be. We have a third configuration point that's right here. That adjusts in a very different way in terms of what it looks like for the motion of this robotic arm. And then we have a fourth and final configuration point here that lifts and raises the entire rest of this arm itself. And so together, by adjusting these 4 control points, we have the ability to move the head of the robotic arm to different locations and be in different orientations, but we would need to plan and figure out how we were going to make those adjustments in order to make that motion possible. So in this case, the configuration of this robotic arm is defined by 4 values. You might imagine angle 1, angle 2, angle 3, and angle 4, describing the angles of each of these 4 points of the configuration of this particular robot. And so now let's start to imagine some of the other constraints that we might need to be thinking about as we're moving robots into the physical world, as we're starting to deal with the real-world implications of trying to navigate about the real world. Imagine that we have this little AI duck robot here, and we have these obstacles that we're trying to avoid, and we're trying to make our way to the goal that's over here to the right. Well, how could we do that? Well, we could imagine that we could probably find a path that gets us from the duck to the goal that is collision-free, that avoids obstacles. And it looks like we've got a few different options, because we're dealing with the real world here. We don't really have a grid in front of us. But we could go there, and then down and to the right, and that might find our way to the star, for example. But what might happen if this physical duck robot were to try to follow that path that we just found? Well, if we tried to follow that path, what you might notice is that we actually collide in some way with these two walls, these two boundaries that I've drawn into our world here. And so our agent, what we were doing is finding a path for us to follow, and in this case, finding a path for like the center of the duck to follow. But because the duck is not a single point, a self-driving car, a robot is not just a single point that we plot geometrically, it's an entire object that has dimensions, that has a physical reality to it. We have to take into consideration that even though we could draw a line that gets us to the destination in this way, if we were to actually follow that path, we're going to end up colliding with some of the obstacles here. And so we need to figure out a way to find a path that will allow the duck to get from its initial position to the goal without colliding into those obstacles. And that's a little bit tricky for a couple of reasons. One reason is this duck is a little bit irregularly shaped, right? There's a bunch of different shapes and curves and angles that are part of this duck that we'd have to try and map out geometrically in order to figure out, like, what does it mean to make sure that no part of this duck avoids an obstacle. It's OK if there's an obstacle here, but if it collides here, then it's a problem, for example. And so we have some challenges to think about. So one simplification we can often make is that rather than try and represent these much more complex shapes, we can try and represent them with simpler shapes instead. That instead of trying to find a way to get this duck to the destination without collision, maybe I'll just find a way to get this circle to the destination without collision. And this circle is a much simpler geometric shape, much easier for the computer to make calculations about. But as long as the circle is bigger than the duck, as long as every point within the duck is also within the circle, then I'm being conservative in my judgment and in my planning. That as long as I can find a way to get the circle to the destination without running into any obstacles, then I will also be able to find a way to get the duck to the destination without running into any obstacles. And if I want to allow myself to be a little bit more precise, to allow myself some more options, maybe instead of one circle, I use multiple circles. If I use multiple circles to define what the duck looks like, or even more circles here, now I've got a bunch of different circles. They're still bigger than the duck. That every point within the duck is still going to be contained inside of one of these circles. But now, by doing a little bit of additional math, I'm still representing these with fairly simple geometric shapes. I can just make sure that I'm going to find a way to make sure this collection of circles can find a way to the destination without running into any obstacles. For now, just to keep things simple, we're going to represent our duck with just this large blue circle, because we know that if there's some way for this large blue circle to find its way to the destination, then we know there's going to be a way for the duck too. And so let's come back to this problem. And now instead of the duck, we'll represent the duck as this big circle. And so the question now is, now we can think about how do we find a way to make sure this circle can get to the destination. Well, before what we were doing is plotting a path for essentially the center of the circle. And where can the center of the circle go in order to get from its starting point to the destination? And we had plotted a path directly through these two boundaries here, these two walls. But in reality, we need to imagine these obstacles as a little bit bigger now to take into consideration the size of the circle, to take into consideration the fact that there are some points where the center of the circle cannot go. For example, the center of the circle could not go right here, right next to this wall, because if you put the center of the circle there, then the entirety of the circle, or some part of it, is going to end up overlapping with the wall. And so what you could imagine doing is taking each of these walls, each of the obstacles, and essentially growing them by some amount, like the radius of the circle, to be able to say, well, this is the set of places where the center of the circle can't go. It ends up being bigger than the wall itself. That if the center of the circle is anywhere in this gray area, it's going to collide with this wall over here. And I can do the same thing for the other walls. I can say, all right, this gray area, if the center of the circle is anywhere there, it's going to collide with this wall here. Same thing for this wall over here. The center of the circle can't go anywhere there. And same thing for the fourth wall down below. And now I have a different looking planning problem where I need to say, how can I get the center of the circle from here to there, not just without colliding with any of the red boundaries, but also without going into any of these gray collision spaces, these states of the configuration where it's going to result in me colliding with one of the walls. And so I could imagine trying to find a path through there. It turns out there is one. It's a different path than the one we found before. But now if I follow this path, I'm sure to avoid the gray areas. And as a result, I'm definitely going to avoid having the circle collide with any of the red walls. And so by taking into consideration the physical reality of the object, how big it is, and adjusting my obstacles accordingly, I can then do a little bit of planning to make sure that I'm able to find a path from the starting point to the destination. I'll take a bit of a pause here, and then we'll pick up from there. One other thing you might have noticed as the problem we've defined it here now is we're no longer working within this fixed static grid where we had these grid of square cells. And we're working with a space where there are lots of possible paths. We didn't necessarily need to follow exact straight lines. And in fact, oftentimes, the straight lines won't always be the path that is going to allow us to avoid obstacles. Sometimes we'll need to make some creative different decisions in terms of going in different directions in order to navigate our way from the starting point to the destination. And so if you have potentially infinitely many different configuration states you can choose from all throughout here, different slight adjustments to the position of the duck or the circle in this case, how could you possibly find a way to get from the beginning to the end in any reasonable amount of time? One common approach is just to sample a bunch of different points inside of the space. So rather than consider every possible point that the circle could be in anywhere on the screen here, I might just start by sampling a bunch of points at random and say, all right, is there a way I can get from my starting point to the destination by going through these points that I've sampled? Now, some of them I definitely won't be able to go through. Any points that are on a red boundary or in the gray area that I know is going to collide with one of these obstacles, those I can immediately eliminate, because those are definitely going to be ones where I'm not going to be able to pass through. But of all the remaining ones, I might then ask, all right, is there a way that I can plan my motion by going through these states that I've sampled from this world of possible states? So for example, I can get from my circle to this state right here. That one seems to be pretty close. And here you can imagine employing some of those search-based algorithms we were talking about before, of figuring out how to navigate between these different nodes in order to find a path to our destination. The one thing we need to take into consideration here is that not every edge between two nodes is going to be valid. If an edge goes through any of these areas that we know are going to result in a collision, we have to avoid those. So for example, from this state, I might like to move to the right to get to that state down there, but that's going to pass through this area, which I know leads to a collision. So I can't do that. Instead, I might have to find my way down to this state over here, From there, I can find my way to that state down below. And then from here, I might like to get close to the star if I'm trying to bias my search in that direction. But again, I can't pass through there. Even though it doesn't directly hit the red obstacle, it passes through the gray area, which is an area where I know if the center of the circle is inside of that gray area, then the circle at some point is going to end up colliding with this obstacle over here. So I can't pass through that edge. But I could get to this edge over here. And then from this edge, I could find my way to that state there, and from there, find my way to the goal. And so by following that path now, I found a path through these states that I sampled that allow me to get to the goal, and so I can find my way and navigate my way to the destination. Now, there definitely are some trade-offs here. Some trade-offs, for example, where I've no longer necessarily found the most efficient path. I've done some random sampling, and so maybe had I chosen some other states, there would have been a path that was even more efficient. And it's also possible that I sampled the wrong states, that I just ended up, based on the particular states that I sampled, there wasn't a path that allowed me to get to the destination. And so you might need to do some additional sampling in order to increase the likelihood that you're able to find a path in order to get to your destination. So what other constraints can we relax here in order to create some more real-world-like scenarios? Well, one other part of the practical reality of the world is that our obstacles are not always going to be like squares and rectangles. So far, every obstacle we've run into has just been like a red square in the grid or a rectangular object that we need to avoid that are sort of simple shapes to be able to figure out how to navigate around. In the real world, things are not always perfect squares and perfect rectangles. They're going to be irregular shapes, things like this, for example, that you might imagine trying to navigate around. And so how could you find a path that's going to avoid navigating your way through any of these obstacles? Well, one common approach is to try and turn something like this into individual cells that we can then try and figure out how to navigate around. We call this cell decomposition. To be able to say, if you were to draw a grid of cells around these obstacles, and then we'll just, again, be conservative and say, to be safe, let's just say that any one of these squares where there's any part of an obstacle, let's call that square off limits. Let's call that square itself an obstacle 2. And so we end up defining all of these gray shaded squares as squares that we can't pass through. Because any square that has an obstacle as part of it, even if it's just a little bit, we're going to call that square an obstacle. And therefore, as long as we can find a path that avoids going through any of these gray squares, we're going to be sure to avoid the obstacles. Now, in this case, if I was trying to find my way from, say, the left side of my screen over here to the right side of my screen, you'll see that it's actually no longer possible. That if based on where the gray states were here, there's no way for me to get from the left to the right, because I would need to be able to pass through these gaps which don't exist because I've said this square is entirely off limits because there's a boundary here. And this square is entirely off limits because there's a boundary here. And so what could I do about that? Well, what we could do is subdivide the grid even further. To say that for any of the squares that have an obstacle in it that are gray right now, let's subdivide those into 4 more squares. And now only highlight the ones where there is an obstacle in that smaller square now. And we end up with something like this. That before, for this grid of 4, all 4 were shaded in. But now that we've subdivided it, we can just shade in these 2 over here. And this space over here is open. We can pass through that because we know that doesn't contain an obstacle. Likewise, for this sequence of 4 here, we shaded in this one in the upper left, and the remaining, those ones were open as well. And so now we can, in fact, find a path that takes us from the left side to the right side by traveling through these states that we know are open. And if that wasn't the case, if there still was no path, we could imagine subdividing even further in order to find out some way of getting from our starting point to our destination. And so now, let's think about a slightly different problem that might come up as we're trying to navigate about the real world. As we're navigating about the world, one thing we've been assuming is that we know where we are. I've been saying the duck is right here, the circle is right there, and we've been able to use that information to plot our path from where we are to where we're trying to go. In reality, it's not always so clear where we are, especially if we're moving and we're having to figure out where we are constantly as we're moving about the world. Well, you might imagine that you can see right here that the car is exactly in this position on my screen. But if you imagine, like, OK, I want to be able to say that the car is right here in this square of the grid, in reality, the car might not know that. It might not know exactly where it is in the world. There are technologies that we can use to try and locate where we are, technologies like GPS, but they aren't perfectly precise. There's some amount of error or uncertainty there. And so in reality, Often we don't necessarily know our position exactly, but we know some kind of probability distribution. We might not know that we're exactly here, but we know that we're kind of around here. What you're seeing is kind of a heat map of where you think we likely are based on the information available to us based on sensors, for example. We think we're probably around here, but there's a chance we're somewhere closer to there, and maybe a small chance we're even a little bit further away, but we're probably not a lot further away, for example. And so rather than represent an exact position, we might have like a cloud of positions where we think we're somewhere around there. But as we get more information in the form of GPS signals or other kind of signal information that we might take in, we can get more precise with our understanding of where we are. We can hone in a little bit and say, now we're much more confident that we're in this region because we're able to gather data from signals and sensors and the like to be able to identify where, in fact, we are. But as soon as we start moving, that too introduces a little bit of uncertainty. That a car might say, I'm going to move forward this amount, and it might know approximately how much it thinks it's moving based on how many times the wheels have turned, for example. But based on the conditions of the road or the weather or obstacles that might be little things in the way, we might be a little bit off in terms of our estimation of how far we've actually moved. So when we move, we might introduce a little bit more uncertainty, where we're, again, not super sure of exactly where we are. We know we've moved a little bit, so we're probably somewhere around there. But it'll take some more sensor data to be able to really refine that and figure out where exactly we are. And so computer scientists have developed a number of techniques for trying to balance between these different sources of information, to be able to understand the physics of motion and where we're going, also understand the sensor data that we're taking in and the potential noise that can come from that. And over time, by collecting multiple instances of data from those sensors, of understanding how far we think we've moved and what the error likely is there, we can end up trying to refine our understanding of where we currently are, and also things like how fast we're moving and how fast we're accelerating, all things that we might want to take into consideration as well. And so what other problems might we try to solve in this world of trying to get AI to navigate about the physical world? Well, we've talked about knowing where we are and knowing where we're going, but we also want to know about the things that are all around us, things like object detection. That if you're a self-driving car, it really matters what's around you in the world, so you can figure out what is the state of all of the street signs, what traffic signals do you need to follow, where are the other cars that happen to be on the road too. And one way that you might gather data about object detection is through visual information. You might imagine that these cars have cameras that are able to look out at the world and take a picture of what they see in front of them. But then we need some way to process that information. Well, we've talked about already that we can use neural networks to do something like this. We've talked about a neural network architecture, the convolutional neural network, that can take a photograph, take an image, process that image, and end up with a classification, some decision we can make about what we think that object probably is. But how could we do that in the context of self-driving cars? What additional capabilities do we want to have? Well, let's think about it. If we imagine looking out at a picture like this, for example, what we want to do is not know just that this is, say, a bridge, but we also want to be able to identify specific objects inside of that image. Essentially, to be able to say that there's a bridge here, there's a particular light there, there's another object that happens to be there, and different objects that appear in this image we want to be able to identify as well. I'll pause here, and I'll pick it up from here in a minute. So we want to be able to identify not just what the photo is, but what we're able to find in specific regions inside the photo. But so far in our convolutional neural networks, we've just been able to take the entire photo as input and then use that in order to determine, is this a photo of this type of object or that type of object, for example. And so there are variants on the convolutional neural network architecture, for example, the region-based convolutional neural network that essentially divides the object detection process into two phases. In the first phase, we take the image, the input that we're seeing from the camera, and we pick a whole bunch of region proposals, essentially draw a whole bunch of boxes inside of that image. And in this case, I've depicted 3. In reality, there might be hundreds or thousands of proposals. And the way we can do that is just by looking at regions that reasonably might be an object. And we can be pretty relaxed about it. We might pick a bunch of things that are not actually an object, but just by looking at pixels that might be similar in color or looking at regions that might be similar to each other, we can compute a whole bunch of region proposals. That maybe this rectangle contains an object we care about, and maybe that rectangle contains an object we care about. And we can do that many, many times. And again, it's OK if some of them or even many of them are wrong. But then what you could imagine doing is taking each of those region proposals and passing them through something like a convolutional neural network. We're able to take a rectangle that contains some particular image and then try to classify what kind of image we think that actually is. And as a result, we'll be able to say which ones do we think actually contain objects, and for the regions that we think actually contain objects, what kind of object do we think it is. Now, in practice, this can be a little bit inefficient. You can imagine if you were drawing, say, thousands of different region proposals and running thousands of different neural networks to be able to calculate what we think they are, and doing that on the fly in real time with new images all the time as you're navigating about the real world, that can start to take a while. And so for that reason, computer scientists have developed some optimizations here to be able to figure out, are there ways we can achieve something similar, but be more efficient about it, to be able to combine them into a single pass of the neural network, or just a couple, for example, to be able to avoid needing to repeat the calculations again and again for constantly having to figure out what kinds of objects are around us. And so that's a way we could get information just from visual data, from something like a photograph, for example. But oftentimes, having access to even more data can be useful too. We might care about not just knowing what is in front of us in terms of what we can see visually, but also to be able to detect distances, for example, to be able to know how close or how far away particular objects are. And so for this kind of thing, we can introduce additional kinds of sensors, additional information that we might want our agent navigating the real world to be able to get. For example, LiDAR, light detection and ranging, where let me fact check that. I'm not 100% sure about that abbreviation. Let me make sure I said that right.
Ranging. Yeah, light detection and ranging.
OK. Ready? OK. So we can use this approach to be able to identify information in front of us, for example, in a photo as we're navigating the real world. But in some cases, we might like additional information too. We might care about not just what objects are in front of us, what can we see, but also what is our distance to objects that happen to be around us, for instance. And for that, we can use additional sensory information, additional sensors that we might add to our agent navigating the world to be able to determine how far away particular objects are. For example, one popular technology is LiDAR, or light detection and ranging. And the idea of LiDAR is that if you imagine that we're a car trying to navigate the real world, and we want to understand how far away are we from other cars that might be around us, what LiDAR will do is it will send a pulse of laser light, and it will essentially bounce it off of objects. And based on how much time it takes to hit an object and then come back, we can calculate essentially how far away that object is. And we can do that at a bunch of different angles. So for example, if we go right in front of us, you could imagine sending out a pulse of light, having it hit an object, and then coming back, and we'll time that. Figure out how much time did it take for the light to hit an object and then come back. And based on that amount of time, we get some understanding for how far away that car is, for example. And we could do that at other angles too, to say how far away is something in this direction. We send out a pulse of light, and it comes back faster. And that tells us that there's an object here that's probably closer to us than an object in this direction as well. And you might imagine doing that at this angle too. That one comes back even faster. That tells us that maybe the closest car to us is this car that happens to be over here. And so we can combine that with visual data that we could process through networks like convolutional neural networks to really develop an understanding for what's around us. And this kind of technology is also helpful, for example, when it's dark out, and therefore what you can see visually with a camera might not be so good, but you can still send out a pulse of light and get it back in order to determine how far away objects potentially are. But it comes back to this overarching theme about artificial intelligence itself, which is this idea that the more data that we have access to, the better conclusions we're able to draw. The more data, the more experience, the more we can learn from, the more we can train these neural networks, use them to develop an understanding of where we are in the world and help us to make decisions. And we've seen in many cases now throughout the course different ways we can take information, give them to the computer, and have them process that information to make predictions, to make decisions, and to figure out what actions to take in the real world. And so hopefully this course has given you an opportunity to explore a wide variety of different applications of artificial intelligence and given you a better understanding for what artificial intelligence is really all about, how it really works, and some of the ideas and strategies and algorithms we use to build these kinds of intelligent capabilities into our computers. So I hope you enjoyed this exploration of artificial intelligence. So that's it for the course. This was Fundamentals of Artificial Intelligence.